Okay, this theorem is basically telling us that if we have a function that is defined for all values of x close to a, so on both sides of it, all right, as you approach a from the right and from the left, if it's defined coming from both sides, then what's going to be true? Well, the limit of the function as x approaches a will exist and be equal to L if and only if the limit of the function as x approaches a from the right is exactly the same as the limit of the function f as x approaches a from the left. Okay, they must exist and be equal to the same value. All right, so let's take a look at this theorem graphically. Okay, so we're going to find three different limits. And for this one, we're going to use the theorem that we just spoke about. All right, so the first one is the limit of this function f as x approaches what a value? 4, right? 4 from the left. Okay, let me go ahead and just write all this down here. From the right, and then finally the limit of the function f of x as x just approaches 4. So let's see what we can come up with here. All right, the limit of this function as x approaches 4 from the left, this is the left. So you just find the curve, you keep approaching x equaling 4, coming from the left. Are we getting closer and closer and closer to a specific y value? Yes, we are. It doesn't have to be equal to it. It doesn't have to be defined here at x equaling 4. But if it's defined everywhere coming from the left approaching 4, then whatever that y value is, that is the answer. So in this case, it's -3. And then what about coming from the right? This one. Well, again, the curve is defined, the function is defined everywhere coming from the right until you get to what y value? -2. So both of these limits do exist, but they're not the same. They don't equal each other, okay? They're not identical. Therefore, this limit does not exist. All right, again, looking at the theorem, this limit does exist. This limit also did exist, but were they equal to the same value? No. One was equal to what? -3, and the other was equal to -2. Those are not the same. Therefore, this limit, as you just approach the value with, from both directions, in other words, does not exist. Okay? You can, are they, just look at it. Are they approaching the same y value, tracing these curves with your finger? Are they homing in? Are your fingers touching at the end? No, they're not touching at the end. Because that's true, this limit will not exist. All right, so let's get through this one pretty quick. All right, same idea. The limit of this function as x approaches 3 from the left first. So here we go. We're approaching x equaling 3 from the left. And yes, we're homing in on what y value? -2, okay? Now, as we approach this 3, x equaling 3 from the right, we are still homing in on what y value? -2. Remember, the existence or non-existence of this point in space has no bearing on the limits, okay? So, because both of these now are the same, then the limit here will be whatever that number is, -2. Again, can you do this? Can you trace from the left and the right and hit your fingers together? Where are your fingers located when you hit them together? Where are they vertically? They're at -2. That's the limit. All right. The next topic of discussion would be continuous functions. And the first thing we're going to look at is the definition of continuity of a function. So a function f is continuous at a number x equals a if the following conditions are satisfied. There are 3 conditions or criteria that must be met to show continuity at a specific x value on the graph of a function. So number 1, the first thing is the function f of that x value a is defined. The second thing is the limit of the function as x approaches a exists. And the third and final condition is that the first 2 conditions are equal to one another. All right, so what would make a function discontinuous? Well, there are 4 types of discontinuities. So letter A is just going to be a hole. It's called a hole. And this is called a jump in the graph of the function. These are specifically called removable discontinuities. Okay, moving to letter C. Here we have another jump in the graph of the function. The limit here would not exist. And in letter D, also a limit would not exist because there's a break in the graph of the function. Both of these discontinuities are called non-removable. Isn't that exciting? Okay, let's look at a couple of examples graphically that deal with the definition of continuity. So, determine the values of x, if any, at which each function is discontinuous. At each number where f is discontinuous, state the condition or conditions for continuity that are violated. So you have to go back to the definition of continuity. All right, that 3-step definition. All right, those 3 conditions right here. You got to know these. All right, here we go. So, first of all, you should be able to look at this and understand it's going to be discontinuous. Okay, it's going to be discontinuous, right? You have a removable discontinuity right here. It's a jump in the graph of the function. All right, but let's go through the definition of continuity. So, number 1, f of what? We're looking at, is it continuous at this x value? That's where something's happening, right? That's where this jump is occurring. Okay, so we want to look at, is f of this x value, -1, defined? And it is. It's equal to 1. So the first condition is met based upon the definition of continuity. Let's look at the second condition. Okay, what about the limit of the function as x approaches this same value, which is -1? Okay, well, here again, we have to be approaching from both sides, and if we do that from the right and from the left, if we can home in on the same y value, then yes, the limit does exist. And in this case, yes, the limit does exist. It doesn't matter if it's defined here. We're looking at a limit. Okay, so that's going to be equal to 2. However, does number 1 match number 2? Does 1 equal 2? No. So you'd say the limit of this function f as x approaches -1 does not equal f of -1 because 2 doesn't equal 1. Therefore, and the 3 dots indicate the word therefore, or conclusion. In other words, therefore, the function f is what? I'll just abbreviate here, is discontinuous at x equaling -1. Okay? So condition number 3 was violated. Condition number 3 was violated. And let's look at a second example dealing with the definition of continuity based upon the graph of a given function. Okay, so let's first determine what? We just go through the 3 steps. That's all you got to do. So f of what? Where is there a break occurring? Okay, this is a non-removable discontinuity. There's a break at -2. So we already know that it's going to be discontinuous, but we should be able to justify that using the definition of continuity. Okay, so f of -2, what's that equal to? Does f of -2 equal anything? Yeah, it's equal to 4, right? 1, 2, 3, 4. So that part is fine. The function does exist at this x value. All right, what about number 2? What about the limit of this function as x approaches -2? Well, you're coming from the left and the right. Are my fingers hitting? Are you homing in on the exact same y value in space? No, you are not. Therefore, this does not exist. As soon as one of these first 2 is D and E, then there's no way 3 can work either. So there's no way. If one of these is D and E, then there's no way that the third condition is going to be true. So we can just go ahead and write this down. All right, so in this case, it is discontinuous. Therefore, what? The function f is discontinuous. It's a D, discontinuous at x equaling -2. Why? Well, because of condition 2 and because of condition 3. Hope you're having fun.